I'm in outer space. I don't know how they talk up here. That's a big planet right there. I think it's that way. Is that way? I'm not sure. I don't know which way it is. Left way? Right way? I don't know. Is this how they sound? Houston, we have a problem. Alright, Earthlings. This one we're going to talk about Rawls' theorem and the mean value theorem. Last year, we definitely did talk about MVT, mean value theorem. We did not really talk about the Rawls theorem. Actually, Rawls theorem was on one of the tests, on one of the free responses that I gave you in class. I forget what unit it was, maybe unit 5 or 6? 5 maybe. And I said, don't worry about it, it's not going to be on the AP test, and lo and behold, it wasn't. But figured in Calc BC we can at least talk about it now. So the Rawls theorem, if f is continuous on the closed interval a to b and differentiable on the open interval a to b. Okay, hopefully we know the difference between closed interval and open interval. It means in terms of differentiability and continuity. If, it's a big if f of a is equal to f of b, then there is at least one number c such that the derivative of it is equal to 0. What does that mean? What does that look like? So if I have, we'll say this function here and this function here. So this is a, this is f of a, and therefore actually this is f of b as well, right? So that's b. F of a and f of b are the same. And they're the same value. So it's saying that in order to get from a to b, it's a continuous function. So what do we know about continuous functions? More than likely, it's not going to be just a straight line. You're going to have a curve to it. And because f of a and f of b are the same value, the function is either going to go up and come back down, or the function is going to go down and come back up. So one example is just to go up and then come back down. That's a terrible up and down. Let's see if I can fix that. Up. Oof, that's janky. I can't. Okay, I'll just make this bigger. Okay, there we go. And so because it goes up and comes back down, there is a derivative here where f prime of c is equal to 0. So this is the c value, okay, and therefore the derivative of it is equal to 0. Because it's saying that in order to be continuous, it's just not going to stay flat. You know, polynomial functions never stay flat, right? It's going to move, okay? And so because I have two values that are the same y value, all right, and they're spread apart or on the interval, all right, the function is going to go up and come back down, or down and come back up. So that's what Rawls' theorem means. This is a special case of the mean value theorem. I'm sorry, not the mean, but the intermediate value theorem. This is the special case of an intermediate value theorem, where, remember, intermediate value theorem basically say if I have a function that this is a and this is b, then there's going to be some c in between those two values on this interval. So here I can say that's c. Okay, this is a special case of that intermediate value theorem. All right. Some examples. What? Okay, so show that Rawls' theorem applies to this function on this interval, and then find the value of c guaranteed by the theorem. So I got to find first. I got to find f of 1. F of 1 is 1 minus 3 plus 2, so that's negative 2 plus 2 is 0. And then f of 2 is equal to 4 minus 6 plus 2, and that's also equal to 0. So because f of 1 is equal to f of 2, we know that we have to apply Rawls' theorem. The reason why is because this is a continuous function and this is a closed interval. This is continuous because it's a polynomial, and polynomials are always continuous. Always, always, always. So how do I do this? Well, what I want to do, f of 1, that's not, okay. So therefore, I got to take the derivative of f of x. I got to find out if it equals 0 somewhere. Well, it should, because Rawls' theorem is going to apply, right? So this is equal to 2x minus 3 minus 3. And I got to set this equal to 0. So the first derivative is equal to 0, and x is equal to 3 halves. So this is the value at which the function is going to reach the maximum or minimum. We don't know if it's a min or max. If I actually plugged 3/2 in, I can get a value, and I don't think, I don't need to do that. That's not a big deal. If I plugged it in, I don't even know what I would get. But actually, I will tell you that the function is going to look like this. So that's going to be a minimum at 3/2. Okay. Actually, it's a terrible graph of the function. It crosses at 1 and 2, so 1 and 2, and then it's going to go like this. So it is a minimum at 3/2. Okay. But that's how you do this. It's basically the same thing as what we talked about doing before, but now I want to find that value of c. So f of 1 is equal to f of 2, and therefore, because it's continuous, UOUS, and differentiable, we know that Rawls' theorem applies. And then we have to find the derivative, set it equal to 0, solve it, and then this is the value of c such that be guaranteed to produce the derivative equals 0 on that interval. Okay, so that's Rawls' theorem. Let's get to mean value theorem, and let's get moving. So mean value theorem basically says if it's continuous on the closed interval and differentiable on that open interval, there exists a c such that the derivative is equal to the secant line, right? The slope of the secant line. So this is what it means. So this is the derivative. This is the secant line. So remember, the derivative is what we call instantaneous velocity. Instantaneous velocity. And then this here is the slope of the secant line. Secant line, which is what we call average velocity. I don't know what that was supposed to be. I'll just do this. Average velocity. Okay, and so that's what we're saying. We're saying the derivative is equal to slope of the secant line. Instantaneous velocity is equal to average velocity. Okay, this means there exists at least one point on the interval a to b open interval where the slope of the tangent line is equal to the slope of the secant line. Boom. See? And I'm like ahead of you guys already. This also means that there exists at least one point where the instantaneous slope is equal to the average slope. Man, I'm a boss. So this is what it's saying. And so if from a to b, okay, this is f of a, f of b. So if I take the slope of the secant line between those 2 points, if I just draw a line, so whatever that slope is, then I can find somewhere on that interval that there is going to be the same slope of the tangent line at some value c. And we want to find that value c. All right, and that's what we're going to be doing next. So, some examples. Suppose that we know f of x is continuous and differentiable on 6/15, closed interval. We also know that f of 6 equals -2 and f prime of x is less than or equal to 10 on the whole interval. What is the largest possible value for f of 15? The largest possible value. Well, what we do not know is we don't know what f of 15 is, right? And so what we have to do is we got to find slope. So f of 15 minus f of 6 is over 15 minus 6, which is less than or equal to 10, right? Because we know the whole interval, the derivative is less than 10. So now, because I have 15 and 6, I know what the x values are, and this is supposed to be f, oof, that's terrible, it's supposed to be a 6. Sorry. And so we know what f of 6 is because it tells us. We have everything else except f of 15. And all we're doing now is just solving for f of 15. So f of 15 minus, we know that's -2, so it's really +2, over 9 is less than or equal to 10. F of 15 plus 2 less than or equal to 90. So then, therefore, f of 15 is going to be less than or equal to 88. Okay, f of 15, there you go. That was just a simple manipulation problem. It wasn't really any meat to that one at all. We just might not have understood what it was asking. Okay. Determine all the numbers c which satisfy the conclusion of the mean value theorem. So what we have to do is we have to find the slope of the secant line. So I want to find what f of -1 is. F of -1 is 2. F of 2 is 14. So if I find the slope here, I got 14 minus 2 over 2 plus 1 equals 12 over 3, so that's 4. So this is the slope of the secant line. between those 2 points. So now what I want to do is I want to find the instantaneous velocity, so that means the derivative. Okay, find the derivative. So the derivative there is going to be 3x squared plus 4x minus 1. So this is the derivative. I want to set that equal to the instantaneous velocity, which is 4. I'm sorry, with the average velocity, which is 4. Now I want to solve it. So this is a quadratic, right? I can bring over that 4. So I get 3x squared plus 4x minus 5 equals 0. Let's see if I can factor it. I don't think I can. I might be able to, but I can't. So we're going to use either a quadratic formula, which I don't recommend, because you have probably a graphing calculator. So what you would probably do is you would graph this into y1. You would find out where the graph is going to touch the x-axis in both spots. And in this case, x is equal to let's see, x equals 0.786, and x is equal to x equals negative 2.120. You can just put it as 1,2, that's fine, but I'm guessing it might round in the third place. I'm not going to pull up my calculator, you can do that by now. So in this case, we have two values, right? Well, we need to know which ones satisfy. Maybe both of them will, I don't know, but how do we determine that? We look at the values and which ones are in the interval. 0.76 is the only one on the inside of that interval, so this is the value of c. So c is equal to 0.786. So yes, we got x equals, but really it's the value of c. Find the numbers of c, 0.786. Okay? Remember, we got to go 3 places. We either got to truncate at 3 or round to 3. We could write 4, 5, a million places, that's fine, but anything less than 3, it's automatically wrong. Alright, Benjamin rides a unicycle back and forth along a straight east-west track. Dude's a boss riding a unicycle. The twice differentiable function b models Ben's position on the track. The table below shows values of b of t and Ben's velocity v of t. For between 40 and 60, there must be a time t when Ben's velocity is 2 meters per second. Justify your answer. So we have to find out basically the slope of this stuff, right? So the slope of the secant line is going to be b of 60 minus b of 40 all over 60 minus 40. This is going to be equal to some velocity at some value, c. Okay, so v of c. All right, I guess you could write v of t, v of c, that v of x, that doesn't really matter right now, but as long as you understand that we're looking for that value of c. Okay, so I just basically plug the values in. So b of 60 is 49, so 49 minus b of 40 is 9 over 20. I get 40 over 20, which is equal to 2. Okay, so 2 is equal to some v of c. Because, so now we got to explain ourselves. This is the justification. Because b of t is differentiable, because it says it's twice differentiable. Now, because it's twice differentiable, what does that mean? This implies continuity. You have to write all this. You can't just take it for granted that everybody knows what you're talking about. Because it's differentiable, it implies continuity. The mean value theorem guarantees. I always spell guarantees wrong. I think that's spelled right. Mainly because I cheated. Guarantees of a time c, okay, in the interval such that v of t is equal to 2. Because we just showed it right there. Okay, there's some value that's going to equal 2. Now, if you used 0 and 10, so I used 60 and 40 because those are my intervals. Okay, I'm not going to use 0 and 10 because that's not in my interval that it told me to use. It could have maybe have told you 0 to 60. What if it said 0 to 60 here? Okay, if it said 0 to 60, then what you're going to do is you're going to try to find 0 to 60 and see what happens. Do the math there. You're going to try to find 0 to 10, 0 to 40. You're going to try to find 2 somewhere. It just so happened that it was 40 and 60, and that was just what it came out to be. But It might be a little harder where you actually have to, you know, figure out a little bit more stuff going on. But for the most part, this one actually wasn't too bad. So that's it for this one, I think. I don't think there's any more. There's not. On to the next one. I don't even know what the next one is. Let's see what the next one is. Oh, increasing, decreasing first derivative test. Now we're going to get actually to the first derivative test. And that one there, we talked a little bit about it last section, but now we'll get to the whole thing next time. Deuces.